Hey class, Mr. Moynihan here with a little lesson on a topic we'll be talking about for the next couple of days called expected value. You can think of expected value as answers to two of these questions, although there's a lot of other ways to think about it too. One way to think about it is, what's a fair price for this particular game or investment or bet? And another way to think about it is, how much should you expect to retain or gain or earn over a period of time? So if you have certain possible results and those results have certain probabilities and they vary in how much they're worth, then the question is, how much would you expect? What single number can you expect to estimate? So let's see if we can actually learn by doing through the following example, dealing with a raffle. So suppose there are 500 raffle tickets, and it has the following prizes: one prize for $500, two prizes worth $200 apiece, and 100 $2 prizes. The question is, what is a fair price for a ticket? So it'll be worthwhile to actually list out how much each individual ticket is worth on a ticket-by-ticket basis. So of these 500 tickets, there's only one, right, the grand prize winner, worth a bunch of money, right? So number of tickets versus value. There are two tickets that are worth $200, but those are like the second prize tickets. There's a bunch of tickets, 100 of them, that are only worth $2 a piece, but still at least you win some money back. And there are 397 tickets, right, the rest of it basically, that are worth nothing. So together, these add up to make $500 tickets, and then these are the values of the prizes on an individual ticket basis, right? So expected value essentially looks like this. And it looks a little scary at first, but I'll help break it down. You can kind of think of this as an average value per ticket. So we're trying to figure out the value of each individual ticket added together divided by 500 tickets in total. So there's one ticket that's worth $500. There are two tickets that are worth $200. There are a bunch of tickets worth $2 a piece, and there are 100 of those. And there are many, many tickets that are worth nothing, and that would be the remaining 397. So just simplifying this a bit, right, we can just use multiplication to make this a little more compact. Now you might think, well, why not just cancel that out? It'll become apparent in just a second. And this part will look a little bit odd in terms of how the division is occurring. So keep in mind that basically what you have is a bunch of individual things being added together, and all of them are divided by 500. So in a way, you can divide each one of them individually by 500, and you can write that like this. You have this one 500 there, you have 200 divided by 500 is right here, and so on. And if you notice, what we essentially have, if you add all these things together, if you do in the calculator, what you get is $2.20. So I'll just spare you the calculation. Believe me, you get $2.20. So that's how much a single raffle ticket should cost on a fair basis, right? If it's a fair game, if there's no profit for the seller. Now, if you notice, what you essentially have here is the amount of money a ticket is worth and the probability of winning that ticket. Likewise, the amount of money a ticket is worth times the probability of winning the ticket. And these things are being added together. The amount of money a winning ticket is worth and the chance of having it, and the amount of money a ticket is worth and the chance of having it. So that brings us to the following formula, if you kind of look at the way this is calculated. So I didn't explain how I came up with this or how this is actually done, but it'll help explain where the formula comes from. The actual formula, which you definitely want to make sure you have written down, says, suppose there are n possible outcomes. So n could be, in this case, 4, right? But in general, some possible number of outcomes. And each of those has an individual probability and an individual payoff. Right? So P sub 1 would be the first outcomes probability, and M sub 1 would be the first outcomes payoff, and so on. So the expected value is simply this formula right here, which looks a bit odd, but if you notice, it's simply the payoff times the probability for one event, the payoff times the probability for the second event, and so on until you've exhausted the number of events. Now you'll notice I have this, what's called summation notation here. You may be familiar with it from Algebra 2. Essentially, this is saying you add up, or sum, this is the Greek letter sigma for sum, from 1 up to n, following this pattern. So 1 goes here, 2 goes there, 3 goes there, all the way until you get to the end, or n here, and then you simply add those things together. So it's a compact way of describing all of this. So essentially, what you have to remember in terms of this formula, how can you sort of understand this, is saying you multiply each payoff or the value with the chance of it happening, and then add all of those things up. So this is a term, this is a term, this is a term, you add them all together. And keep in mind that since these are probabilities, the probabilities of all of our outcomes in our space have to add up to make 1. So you'll notice, if you look back here, you have 1, 2, 100, and 397, all out of 500. If you add those 4 individual probabilities up, you get 100%, or 500 over 500. And then these are the payoffs for those specific events. Okay? So let's do 2 examples here to kind of understand this concept in a bit more detail. The first example deals with attendance at an event. Suppose the attendance for a local theater is very predictable based on the weather. If it's extremely cold, then 395 people will attend. Cold, 450. Mild, 620. And warm, 505. On a particular night, the weather follows these probabilities here for extremely cold, cold, moderate, and warm. I guess I changed the wording here. I guess I should say mild, but you get the idea. The question is, how many people are expected to attend, why did I write game? Show tonight. Lesson learned, proofread these. Anyhow, so the expected value is going to be the sum of all of the individual products. So what I mean by that is it's the sum of the individual products of payoff times probability. How many people are going to attend, and what chance is there of that happening? So let's see. We have a couple of events here. We have 395 people, and that'll occur with a 0.06 probability. We have, what else? We have 450 people attending with a, that's if it's cold, 0.44 probability. We have 620 people with a probability of also 0.44. And we have 505 people with a slim 6.06% chance of occurring. So these 4 terms here basically correspond to the 4 cases here, right? So I won't actually list them out. That's just sort of a way to generalize the formula. But essentially, this is one possibility, and this is the chance of it happening. This is a possibility, and the chance of it happening, and so on. So all you do is to find those 4 products, and then add them together. So if you bear with me on the calculations here, you can actually do these all in one step in the calculator. That might be a little more video friendly. I don't think YouTube has a way easily yet for me to speed these up, so very exciting viewing, I'm sure. So rather than actually list these all out, just for the sake of the video, I'm just going to write them all in here. One single calculation. I can expect 524.8 people to attend. Right? Which, if you look at the numbers, right, in terms of how likely they are to happen, it kind of makes sense. It's somewhere in between these, but it's sort of weighted depending on how many people will attend, if it's warm versus extremely cold. And there you go, 524. I suppose 525, if you want to round up, can't have 28 of a person. One more example, one that's a bit more detailed. So let's say that we're dealing with a carnival game and it costs $4 per play. The game works like this. If you roll a single die, there's plural of dice, just a single 6-sided die, and what you win is the dollars equal to the value you roll. So if you roll a 2, you get $2. If you roll a 6, you get $6. Now if you roll a 1, you get only $1 back even though you paid $4. Right? So you could lose. But that's how games work. The question is this a fairly priced game? Or more specifically, is the cost of the ticket equal to the expected value? So let's go ahead and find the expected value. So the possible outcomes are, well, you could win $1. And how likely is that to happen? Well, a 1/6 probability, because it's a fair dice. You could win $2. I'm going ahead and adding these together. That also occurs with a 1/6 probability because it's a fair dice. And you get the idea. You could win $3, $4, $5, and you could, ideally, win $6. You pay $4, but you earn 6. That would be a nice game. So all you got to do is add these together. Now you might think, well, isn't there a faster way to add these together? Notice that these probabilities back here were different, right? So I had to kind of go in and enter them in step by step by step. Here, if you can find shortcuts in general, especially when you're making videos, it's a useful tactic. And you'll notice that all of these have a 1/6 in them. So I can just factor out that 1/6. And what that leaves me with is 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is much easier to enter that in the calculator than all of these. Because if you then if you distribute, or sort of unfactor the way it's described, then you'd have the previous step, right? So that'll be a little bit more viewer-friendly. I just go 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. You get 3.5. Remember, these are all dollars, so it'd be $3.50. So that's how much it would be if there were no profit involved. So that's the expected winnings, basically. You expect to win $3.50 on this game. So does it make sense to pay $4? No, it doesn't. Why? Because this is less than the amount that you pay. If this is how much you expect to earn, and this is how much you pay to do it, it doesn't make sense to play that game, based on just common sense, right? So hopefully you get a better feel for what expected value is. You can kind of think of it as a weighted average. It's chance of something happening times the value of that particular occurrence. So looking back at the formula to close out, just to summarize, you have the products of payoff and probability all being added up. All right, I'll see you in class.